Today, the topic of discussion is error detecting and correcting codes. As we all know, when binary data is transmitted and processed, it is susceptible to noise that can alter or distort its content. This noise can be either a small change in the bit of the data being transmitted, that is, the ones may get changed to zeros and zeros to ones. Because digital systems must be accurate to the digits, errors can pose a serious problem. Several schemes have been devised to detect the occurrence of such errors so that whenever such an error occurs, the concerned binary word can be corrected and transmitted. The errors can occur in single bit or it can occur in multiple bits of data that is being transmitted. So, single bit errors are those errors which occurs on a single bit of the data being transmitted. That is either 0 is changed to 1 or 1 is changed to 0. But next category of errors are called burst errors, where more than one bit have been changed. So we can categorize errors as either a single bit error or a burst error. In the case of a single bit error, if the error for detecting the error, we use a parity for detecting the errors. We can have a pictorial representation of single bit error where this is the data being transmitted, that is 1001011 is the data being transmitted. While transmitting, certain noise occurs, and as a result the bits may change, and if the bit changes and received at the receiving side like 00011011, here we can say that a single bit has been changed. So this is called a single bit error. The simplest technique for detecting errors, that is single bit errors, is by adding an extra bit, and that extra bit is called the parity bit to each of the word that is being transmitted. So in the figure, we can see we have an original data unit where the data is 1001001, and during the transmission itself we will be appending an extra bit, and that extra bit is called the parity bit. So it is a very simple technique used to detect errors, and in parity check a parity bit is added to the data block. So assume that the data block is of k size, then adding a parity bit will result in the block size of k plus 1. So one extra bit is added, which is treated as the parity bit. And the value, so what should be the value of the parity bit, whether it is 0 or 1, is determined by the number of ones in the k bit data blocks. So the value of the parity bit, what should be the value, whether it is 0 or 1, is determined by the type of parity we are following. Suppose if we are following an even parity, the parity can be either an even parity or odd parity. And if we are following an even parity, and if A wants to send the data 1001, in even parity, the number of ones should be even number. Okay, in even parity, the number of ones should be an even number. That is, in the example, A wants to transmit 1001. Here the number of ones is 2, which is an even number. If that is the case, then the parity bit is 0. Okay, so the A will append 0 at the end of the data to be transmitted, that is 10010. So this is the data being transmitted to B. And B receives the data, and the B also computes the parity, that is it also checks for the number of ones in the data being received. Since it is following an even parity, it checks for whether the number of ones is even. And if B computes the result as even, then B reports correct transmission, otherwise B reports an error. Okay, and coming to the odd parity, and same case, if A wants to transmit the data 1001, in odd parity the number of ones should be an even number. That is, if 10001 is the data to be transmitted, the number of ones in the data is to be transmitted is 2. Since we are following an odd parity, we have to make the number of ones as odd. And for making the number of ones as odd, we have to append one more 1. Okay, so we have to append one more 1 to make the number of ones as odd. So the even parity bit now becomes 1. Okay, so the data to be transmitted by after appending the parity bit will become 10011. So this is the actual data being transmitted after appending the parity bit. And on the receiver side, B computes again the overall parity of the data being received, and if the data being received has the number of ones as odd number, then B reports correct transmission, else B reports an error. For detecting single bit errors, we use parity, and for detecting and correcting multiple bit errors, we use Hamming code. Hamming code is not covered in depth in this topic. So the next topic is alphanumeric codes. So far we have studied about various binary codes used for representing numeric data. But as we all know, computer should be able to understand alphabetic characters, and it should also understand other special types of characters. So alphanumeric codes are used where it is used to encode the characters of an alphabet in addition to the decimal digits, and they are used primarily for transmitting data between computer and its input output devices such as printers, keyboards, and video display terminals. And so the most common types of alphanumeric codes used are ASCII, ASCII. It is pronounced as ASCII, ASKEE. And the abbreviation for ASCII is American Standard Code for Information Interchange. It is a 7-bit representation and is most widely used. Since this is a 7-bit code, the number of bit patterns that can be created with 7 bit is 2 raised to 7, which is equal to 128. And this ASCII code can be used to encode both the lowercase and uppercase characters of alphabet, some special symbols, and in addition to that, it also can be used to represent numbers ranging from 0 to 9. It is used extensively for printers and terminals that interface with small computer systems. Next category is EBCDIC. EBCDIC, EBCDIC. EBCDIC. It is pronounced as EBCDIC, and it is an 8-bit alphanumeric code. Since this is an 8-bit code, it can represent 2 raised to 8, which is equal to 256 bit patterns. And it encodes many other symbols too, other than the characters and symbols. It is used by most large computers to communicate in alphanumeric data. Since ASCII is the widely used alphanumeric code, we can have a symbol familiarization of this ASCII code groups. So the table shows the ASCII code group where they are listed with the 3 most significant bits of each group along the top row and 4 least significant bits along the left column. And suppose if I want to represent capital letter H, so this is a 2-dimensional representation of the ASCII codes. And if I want to represent H is represented as what is the most significant bits correspondingly column wise. The most significant bit is 100, and the leftmost row wise the value is 1000. So the H is represented as 100100.